Thank you. So I want to switch gears a little bit and tell you about what I've been thinking, spending some time thinking about, which is how do we identify the closest supernova in the legacy survey of space and time? And I will be using this supernova that you can see down here, supernova 2023 IXF, which went off in the beautiful galaxy M101. And so because it was in M101, we collected a really fantastic data set, both after discovery and with pre-discovery serendipitous observations. And so I'm going to say this is fairly rare. It's a once in a decade. I put an asterisk. That is a very loose term. But having this type of data set is extremely unusual and requires early discovery, which is something that I think that LSST could excel at. So I just want to show you some of the things that made this unique. I'm going to start with the spectra here. So this is looking at the evolution over 2 nights of the spectra. You can see these narrow emission lines. That's telling us that we have circumstellar material that's pretty dense around the star that exploded. And these disappear within the first few days to 1 week after explosion. So without discovering this early, you would never get that evolution. Without discovering it really early, you wouldn't be able to see this kind of evolution where these lines disappear over the course of a night. Looking at the light curve, this is just 12 days of data, and you can see that we had very high cadence multiband sampling. This is something that LSST won't be doing, but if they tell us about a supernova like this, discovered way down here, then we can turn other telescopes, other ground-based surveys to get this type of light curve. And then the other thing I want to point out here is all of these open points here, these open diamonds are coming from amateur astronomers who happen to be observing M101 pre-discovery. So we got a beautiful picture of this very early rise from the amateur astronomy community. So a supernova like this, the most information and the biggest discovery space for us is having very early data. But we need to know that it's this type of supernova. So the rest of my talk is going to be kind of focusing on how can we do that, and then also asking questions of you of like, do you have ideas of how we can do this? And so just to highlight how important this was, in the last year, there have been 28 refereed publications on Supernova 2023 IXF, covering everything from searching for neutrinos to whether there was gamma ray flux, X-rays, UV observations, all the way through radio detections, and then 79 non-refereed notes about it. So you can see the ADS chart. This is a significant event. So some things that I think enabled this to be so successful was first the public announcement of the discovery within 4 hours of the image. This is something that Ruben will do even better. So we should have something within a minute of a discovery. There was also a rapid classification. So within 2 hours of the discovery announcement, it was classified as this unique flash ionization feature supernova. This is something that I think is probably one of the biggest challenges is how do we identify what is interesting? And then the third thing, which I wanted to highlight, is that there was a lot of community sharing of information via the transient name server as well as via ATELs. So these are all the different astro notes that were submitted about Supernova 2023 IXF. So as people looked at their X-ray data and saw a detection or didn't see a detection, they reported it. As people went back and looked at their prior photometry, they reported numbers. So there was a lot of information that was shared in the early phases of this that went on to become publications. So 2 things that I think Ruben can contribute to this conversation and our understanding of this type of supernova and these objects. The first is what is going on before the star explodes. So this is looking at 23IXF as the solid circles and a couple other supernovae, both that had pre-supernova explosion detection, so some kind of outburst before explosion, and then our search for them with 23IXF, and then what Ruben's limits are going to be. So you can see that Ruben's going to go much fainter, and we're going to have this 10-year baseline that we can look for potential outbursts. And that could tell us about how that material got around the star before it exploded. And then we'll hopefully see kind of the supernova explosion itself. The other thing is looking at the very early time light curve. So this solid line is what we expected the light curve to do. This is kind of the typical modeling that's done. And then this is the actually what was observed. So you can see that the rise was much slower than we were anticipating. And this is maybe like the first time, the second time this type of rise has been seen. And so we're trying to understand, is that normal? Is it abnormal? And if Rubin is alerting us to a supernova way down here, we can start to observe this line as it becomes visible to other supernovae. But again, we have to know that it's this interesting supernova. So with that, I want to talk about what the basic workflow I envision with Rubin is and where I think different parts of the infrastructure come in. So the current plan is to have a single 30-second visit. This could be divided into two 15-second images or just a single image. And the hope is that in either of these scenarios, we're definitely ruling out cosmic rays. So the transients reported are real transients. And an alert is issued within 60 seconds of this observation. So we know very quickly what that is. A second image will be obtained of the same field in a different filter 30 minutes later. This will give us color information as well as possibly information on the rise if we have a good model of what we expect this early data to look like in different filters. So this is kind of, I would say, like the best case scenario. We're looking at this rapid rise. This is what we would expect the rise to look like in the same filter for two observations spaced 30 minutes apart. So it's possible that you could see this rise, but I'll show you that that gets more complicated when we start talking about different filters. Within an alert packet, there's if this is the first time this source has ever been detected, there's very minimal information, and this is to enable that to get to us as quickly as possible. So you get a measure of brightness, a measure of extendedness, a kind of real bogus measurement that's called spuriousness, which filter was observed in, and its coordinates. So you can imagine using coordinates to say, you know, if this is in the galactic plane, maybe you think it's more likely to be like a nova or something like that. So because you get such little information in the alert packets, the additional information that different brokers add, I think, is going to be very important. So these are all of the different defined brokers. And from these, we will get host associations, cross-matching with existing catalogs. So what are the potential hosts? What is this a known source? Is it a variable star? Is it an AGN? There's also some attempts to do classifications at different stages of the observing process. Some of it is just looking at a single image. Is this near a galaxy, but not directly in the middle of a galaxy? That would indicate maybe it was a supernova. But then they also give you the ability to define your own filters on color and rise. So I think getting this type of added information from the brokers as quickly as possible is also key. I know reading through the documentation, some of them were like, oh, within 12 hours, this will be available. For I think the rise of a supernova, those 12 hours are critical. Okay, so that's my vision. Now I want to get into some of the challenges, which I don't necessarily have answers to, but I'd love to hear your thoughts on. So the first is just a question of what is real and what do we consider worthy of follow-up. So this is again coming back to Supernova 2023 IXF. This is its discovery observation, but it was actually found and observed by ZTF almost 12 hours earlier. It was determined to be very real, but a second image was never taken. I think like the weather went bad. And so we didn't get like a confirmation image. And then the different brokers did see this, they identified it, but they either like didn't have the human power to vet it immediately, or it was classified as more likely to be bogus. So when we think about what our classification schemes look like, I think we need to think about, you know, what would a very nearby supernova look like? And would we say, oh, that's just too bright, you know, that's unlikely to be real, or something like that? Or it's, oh, so far away from the host because it's like 6 arc minutes away from the host, but actually for a nearby galaxy, 6 arc minutes is still in the galaxy. So we need to think about like what are the outlier scenarios for very nearby objects. So another challenge that I mentioned earlier is how do we define a rise? So this is another nearby supernova 2024 GGI. Look for a paper on the archive early next week for this. And we got a super high cadence multiband light curve for this, less than a day after explosion. So I have hours after explosion on this x-axis, and each of these pairs are observations that are taken half an hour apart. So this is simulating what we'll get with LSST in G and R band. And what you can see is that this supernova is actually evolving to be bluer and bluer with time. And so that means that we actually, if we took R and then G band, you would get a decline in brightness over half an hour. If you took it at 17 or 18 hours, but if you took it at 21 hours, maybe you would see a rise. So really understanding what these light curves are doing at early times in different colors is critical to being able to say, is this supernova rising or not? And then I guess one of the final things I want to say is just, is it a supernova? As we push down to fainter and fainter brightnesses, discovering these things earlier and earlier, we're moving into territory of LBV eruptions, of luminous red novae. And so understanding again what each of these look like in different colors at early times is important. That means that we need very deep early data. I'm not sure if we have this yet, or if this is something like the first year of Rubin will really help us define, and then we can incorporate that information afterwards. One piece that would help with this is if we had progenitor information. So having catalogs from archival images, I'm thinking space-based for super high resolution that gave us lists of red supergiants, lists of luminous blue variables, would help us identify, if the supernova or the source is coincident with a red supergiant, I feel pretty confident that's a type 2 supernova. And this is what the red supergiant progenitor SED looked like for 23 IXF. And I want to say that as funding gets cut for some of these space missions, it becomes I think teams are less likely to do the community service of outputting a catalog that isn't necessarily their science. So I want to really plug the importance of funding these types of catalogs. That's the end of my talk. I think this is going to be challenging with Rubin, but and possibly we could make a case here for tweaking the cadence. I know Fed said earlier that it's not set; it's still like tweakable. So if that was those observations were an hour apart, I think identifying that rise would be much easier. And I want to highlight what the brokers are going to add, that we need this auxiliary information to be able to make this call. But we still have these open challenges of when do you call something a supernova? How do we determine whether it's rising or not? How do we determine whether it's a supernova or some other faint contaminant? And then make a call for having different progenitor catalogs. So thank